Let's look at some examples of one-dimensional elastic collisions with no external forces between two particles. So suppose I have particle 1 and particle 2, and we have them moving on a frictionless surface. And let's choose a reference frame, in which we'll call the laboratory frame, in which the initial velocity of particle 2 is 0. So our frame is called the laboratory frame. And in this frame, we're thinking of particle 2 as our target. And the target is at rest, and particle 1 is moving in with some initial velocity. And so here is our initial picture. And then in our final state, both the target and the particles can be moving. So we'll just indicate v1 final. And we'll have the target is also moving with v2 final. And we have I hat. So let's now look at some examples where we're analyzing this type of collision in which both energy and momentum are constant. And for a particular example that we'll want to look at, we'll have m2 is twice m1. Now, for our two equations that we're going to write about, we'll choose components, and we'll write our energy equation as 1/2 m1 v1 x initial squared plus 1/2 m2. So now we're going to write 2m1. But the object 2 is at rest, so we don't have to worry about that one yet. And so our initial kinetic energy is just equal to the final kinetic energy, 1/2 m1 v1 x final squared. And now I'm going to substitute in 2m1 for the mass of m2, v2 x final squared. And that's our energy condition. And then our momentum condition is that the incoming momentum, 1/2 x initial, is equal to the outgoing momentum, m1 v1 x final. And again, I'm going to substitute for m2. That's 2m1 v2 x final. And these two equations represent a system of two equations with two unknowns. We'll treat this as givens along with the initial velocity of particle 1. And our target here is to solve for v1 x final and v2 x final. So we have two equations and two unknowns. Now it's a quadratic equation. So we have to identify, from a problem-solving strategy, we have to identify which quantity we're going to solve first. And so let's solve for v1 x final, which means we need to eliminate v2 x final. And the way I'll eliminate v2 x final is I'll use the momentum equation. And notice that the m's will cancel in the momentum equation. And so if I divide through by 2m in the momentum equation and bring this term over to the other side, equation 2a becomes v2 x final equals, I'm dividing through by 2, 1/2 v1 x initial minus 1/2 v1 x final. So this gives me a target, v2 x final. I can substitute into there. This equation, again, can be cleaned up. Let's clean it up before. We can get rid of the halves. We can get rid of the m1s. And so the quadratic equation that we're going to be working with is v1 x initial squared equals v1 x final squared. And I'm dividing through by 2, so I have a factor 2 plus 2 v2 x final squared. Now that's our energy equation. And here's our momentum equation. So if we substitute this in and square it, we can now substitute, and we get v1 x initial squared equals v1 x final squared plus 2. Now we make our substitution. So that's 1/2 v1 x initial minus 1/2 v1 x final, quantity squared. So let's now expand this. And we have to be careful not to make any mistakes. v1 x initial squared equals v1 x final squared. Now, if I pull the 2 out, I get a quarter in front and divide that by a half. So I get 1/2 v1x initial squared plus another one plus a 1/2 v1x final squared. Those represent the squaring out those two terms. Now the cross term will have a factor of half in the front, but a factor of 2. So we have a simple cross term of v1x initial, v1x final. Now, let's collect terms. Let's bring everything over to this side. So we have a 0 equals 3/2 v1x final squared minus 1/2 v1x initial squared and minus v1x initial, v1x final. Now, I always like to just write this up in a simple way to use the quadratic formula. So I'm going to divide through by 2/3, and I get minus 1/3 v1x initial squared minus 2/3 v1x initial, v1x final. And this is now a simple application of the quadratic formula. Negative b is plus 2/3 v1x initial, plus or minus, and we're going to interpret those two roots in a moment. We have the factor 2/3 v1x initial squared minus 4ac. So that's another minus sign with a plus. So that's plus 4/3 v1x initial squared, all to the square root, and everything divided by 2. Now here, let's just look at this factor. This is 4/9 plus 4/3. 4/3 is 12/9, so that's 16/9, which is very convenient, because when you take the square root, that's 4/3. So we get equal to 2/3 v1x initial plus or minus 4/3 v1x initial divided by 2. Now, we see that there's two different roots. So when you add them, you get 2 v1x initial divided by 2. So there's one solution. And when you subtract them, you're getting 2/3 minus 4/3. That's negative 2/3 divided by 2. So that is another solution, v1x final equals negative 1/3 v1x initial. Now, let's think about the meaning of these two possible solutions. This solution has v1x final equals v1x initial. So that's the initial conditions, just repeated. And that will always be the case. One solution will describe the initial state, and the other solution will define the final state. You can check for yourself that if you just put vx1 final into this equal to vx1 in the initial into this momentum equation, then v2x final is 0, which just repeats the initial conditions. So this solution is the initial state. And this solution here is the final state. Now, just to complete the picture, v2x final, well, that's equal to 1/2 v1x initial minus 1/2 times v1x final. But v1x final is negative 1/3. So we have a half minus 1/2 times minus 1/3. So that's a half plus a sixth, which is 4/6 or 2/3 vx initial. So that's 2/3 v1x initial. And that represents the solution to this particular problem. Now, of course, what you want to do is you want to check. We know the momentum condition is already satisfied, but just as a check, you would like to put it into the energy condition just to make sure that when you square these things out, you get the right terms. However, we're very confident of our result because we've already reproduced the initial conditions, and that wouldn't happen if we made some algebraic mistake. So that by itself is a sufficient check that this is a correct solution. One thing we should sit back and think about is that when we use the energy and momentum, that we're inevitably dealing with quadratics, and so we expect to solve a quadratic equation at one point, and here it was right here. Now we're going to find another way to do this by linearizing the system, which will be a lot easier.